Example, multiplication rule for probability number 1. You are president of a club with 10 members, 6 seniors and 4 juniors. You need to choose 2 members to represent the club on 2 committees. The first person selected will be on the awards committee, and the second will be on the orientation committee. The same person cannot be selected for both. You decide to select these representatives at random. What is the probability that a senior is chosen for both positions? A key fact here is that the same person cannot be selected for both. We actually call this an event or a selection without replacement. Once we remove a senior from the group, we no longer can select them again, and so the sample space actually changes. So to begin with, there are 10 people. But let's choose a person for the first group. For the first position in the awards committee, there are 10 students to select from and 6 seniors, so it's a 6/10 probability for that first one. Now that we know that a senior has been removed, what's the probability that a senior is chosen for the orientation committee? Well, now there are only 5 seniors left to select from, and there are 9 students total. So we have 6/10 multiplied by 5/9. Now if we multiply these, that'll be 30 out of 90, which reduces to 1/3. The probability is 1/3 that a senior is chosen for both positions. Example, multiplication rule for probability number 2. If a container has 3 red balls, 5 white balls, 4 black balls, and 1 yellow ball, what is the probability that you will draw, or that you draw without replacement? And part A is 2 black balls. So in this situation, we are going to think of this as being 2 consecutive draws. You're really reaching in and pulling 2 at the same time. But we're going to think of it as selecting 1 at a time. So the first fraction would be the number of ways we could, or the probability that we could draw a black ball on that first pull. Well, there are 4 black balls out of, let's see, 3 plus 5 is 8, plus 4 is 12, out of 13. So 4 out of 13 for the first pull. And now that we've removed 1 black ball from this, there are only 3 left. So it's 3 out of 12. And that's because it is without replacement. So 4/13 multiplied by 3/12. If we multiply that across, that is 12 out of 156, which reduces to 1 out of 13. Part B. A red ball given the first ball was black. Now this is a different situation because we don't actually care about, we're not drawing 2 balls here. At first glance it looks like we're drawing a black and then a red, but we already know that a black has been removed. So the chance that we get a red ball at this point would be there 3 out of 12, or 1/4. That information tells us there's already been a black ball removed, so what's the chance of getting a red? So the sample space has changed fundamentally. Part C, 2 yellow balls. So to consider this, we notice that there is 1 yellow ball, so 1 out of 13 is the chance on the first pull we get a yellow, multiplied by, there are now 0 out of 12. So 1 out of 13 times 0 out of 12, which is 0. It is impossible to draw 2 yellow balls because there is only 1 in the container. Example, multiplication rule for probability number 3. You have a dozen donuts, where 10 are glazed and 2 are chocolate. You randomly eat a donut, and then eat a second donut. What is the probability both donuts were chocolate? Now this explicitly tells us that we eat the donut, so clearly we don't put it back. But there are other problems you might run into where it is still without replacement. However, we have to assume that it's been eaten or it's been removed entirely. Right. So in this case, we first need to consider the probability that the first was chocolate. Well, because there are 2 chocolate out of a box of 12, that is 2/12 for the first probability of getting a chocolate for the first. And now that we've eaten this chocolate donut, there is 1 remaining out of 11, and 2/12 times 1/11th, that multiplies to be 2 out of 132, which reduces to be 1 out of 66. That is the probability of getting 2 chocolate donuts.